Occasionally I forget to turn on the streaming, but not in this class because I think if I do forget, a lot of people would remind me, go like, "Hey, Tack, you need to turn on the streaming to YouTube." But I need
Yeah,
to
it
post.
seems someone always notices within a few minutes.
Yep, there we go. I'm just copy and pasting the link, but since it's a public stream, you guys can all just go to the YouTube and find it over there. But I'm gonna post the link in Discord. And somebody has been telling me that Discord has been unreliable today. No doubt it has to do with not going through with a deal to sell to Microsoft. Yeah, I know what most people are tracking in terms of the news, but I got some other stuff to track too. Alright, so I just posted the link and it doesn't do the normal thing of giving me a preview of the YouTube screen, because normally it does. Go ahead.
YouTube is good.
Oh, okay. Yeah, but the presentation on Discord text channel is a little bit different. Just a little different, that's all. Alright, so the stream is ongoing. I'm just double checking on YouTube. And well, aren't you guys glad that Discord did not sell to Microsoft? At least not yet. For $10 billion. That's kind of interesting.
It's a lot of money to turn down.
It is. On the other hand, pretty sure there's a reason why they turn it down. Well, Oracle is interesting, but I don't think Oracle has any need to buy Discord. Unless it just wants to piss off all the gamers. I mean, sure, go ahead, piss off all the gamers. That is true. That is true with TikTok. Yeah, I think we are getting back into the phase back in maybe 1999 or 1998 or so. Tech was booming. All the large companies are just buying the small companies left and right, and then they could not figure out what to do with their purchase. Yeah, it looks like you know we're in that phase of the cycle right now. Big companies just they made so much money, they just want to buy a solution instead of developing a solution. That's usually not a good sign. Microsoft did that a lot, back in those days, and it did not serve Microsoft well, though. Yes. Well, at least Apple is making the M1 chip. I looked into that, and that's actually quite impressive. Um, oh, why does why would Steam lawyers have a field day today? Yeah, Microsoft has Skype already, and they're not doing very well with Skype because
And Teams.
and Teams exactly. It's like how many different platforms do you need for communication from the same company? I mean, Google is getting there already too. I mean, Google has multiple platforms, and at least they try to migrate people from one product to the future product. Um, and these companies basically, I think it has to do with the companies getting so large, it cannot coordinate um, the products that they're making. Oh, the graveyard. Yeah, yeah. That is true, but a lot of the platforms that Google destroy are Google's own platforms too. If you just look into their products, they split and then they merge, they split and then they merge. You can look into there's a diagram called I cannot remember what the diagram is called, but it has to do with how patents were created in different companies, and they draw these links. Each line is representing a collaboration link. And if you look at the Apple one, it's very centralized. There were a few really key people in charge of determining which patent should be applied and which one not to apply and stuff like that. With Google, it is completely disorganized. It's just all over the place. So the culture of the two companies are really very different. I know their products are different too, but as a high-tech company, I think it's interesting how their management is also entirely different. Google is very, very decentralized. So that's kind of interesting. All right. Okay, so I think it's time to get started. So you guys got the extra 5 days-ish, to do the homework assignment, and it was kind of interesting to see that some people just kind of procrastinated for another 5 days and then did almost the same thing as last Wednesday. No, excuse me, last Thursday. So that was kind of interesting. But I do hope this program help you guys to understand, how to use TTPASM to solve problems, to basically implement C code. So the first thing I'm going to do today is really just to give you my solution to this particular program, and I'll explain along how I write the code. So we'll first do that, unless enough people say no, Tech, we don't need to do that. Let's just move ahead and talk about recursion. So that can happen too. Okay, so it looks like most people are just participating in the Apple versus Google versus Steam discussion. Oh, okay. All right, I'm gonna put it on the side. All right. So okay, how do you know your code works? Okay, so that is a big question. I know it doesn't sound like a big question, but it really is a big question. So let me go ahead and, because I'm not looking at the end result, I'm not just looking at the end result of whether the 2 bytes are exchanged. Because if we really just want to exchange the 2 bytes, there are shortcuts to do it. I'm really looking into whether the swap subroutine is implemented correctly or not. So I'm looking at the assembly code and see whether it is consistent with the C code. That is how this assignment is going to be graded. So what I'll do is I'm just going to go to the source code of swap and start with that. And I noticed that some people are interested in getting the syntax highlighting part to work, so that's good too. Alright, I'm just searching through my own questions to find the source code of. Question 4, thank you. And no, I have no intention to make an extension for VS Code, so VI it is. Alright, so there we go. We got the main here, and this is the swap subroutine. So the main I'm not too worried about. I'm just going to copy and paste it into the program that into the text file that I'll be writing. So I will just go ahead and implement the swap subroutine. And let me see, do I have a command line interface to do that? I'm looking for one that has a larger font, like this one over here. Okay. Alright, so let me move it over here. There we go. Alright, so we'll go ahead and implement swap.ttpasm. There we go. And this is about swap, so we'll go ahead and, so I'll just start with the subroutine swap itself, and then we'll go back and put in the rest of the program. And so that means to be safe, I'm going to put a no up here and then do a jmpi to main. So this way I don't accidentally step into swap, and use it as a starting point of the program. So I almost always just put in the end of the subroutine, which is the return, the code to return to the caller, which is LD. It's always safe to use register B, even though in this case it is also safe to use register A, because swap has no return value, so register A has no special meaning to the caller, because nobody is going to say, oh, what is the return value from swap? Well, swap has no return value. So we'll go ahead and just do it this way. Alright, so I saw some activity in the text channel. Oh, okay. That is interesting. I could fork TTP as open source. I think I can use, I'm too lazy, but I think adding interrupts, and input-output capabilities to TTP is going to be useful, not only to teach this class, but also to in some other context too. So we'll go ahead. Yeah. All right. So now we are into the actual content of swap. So the first thing I usually do is to try to look at the frame and find out what the frame is going to look like. We got two parameters, so we got PTR2, we got PTR1, and then right below PTR1 is the return address, which is pushed by the caller. So here we have the return address, and now we have all the local variables, and we only got one this time. We only got t as our local variable. So depending on how you want to use the labels, so that you can quote unquote make the subroutine more extendable in the future, extensible in the future. So you can use a whole bunch of labels. We can just say t is at the bottom of the entire frame, so it's 0, and then we can say swap underscore local var size is t1 plus, and that has to do with t using just 1 byte. So the 1 is referring to the 1 byte that t is using, because it's an 8-bit integer. And now we can specify where PTR1 is supposed to be at. So we have PTR1 being swap local var size 1 plus, because it is 1 byte on top of the space already used up by local variables. So this way I'm not giving the return address a label, which is reasonable, because there really is no need to know where the return address is, because by the time we need to access the return address, the stack pointer should be pointing back to the return address already. And then PTR2 is PTR1 1 plus, because it is the second argument. Alright, so at this point, okay, I need to emphasize that at this point the stack pointer register D is still pointing to the return address, which was pushed by the caller. So at this point, T does not have its space yet on the stack, and that can only be done using the subroutine's own code to decrement the stack pointer. So this will allocate the local it will allocate the 1 byte for the local variable t. So the more generic way to do this, as I illustrated in the previous classes, is to make use of swap local var size. So I know it is not necessary in this case, but this approach is a whole lot more scalable, so that when you are dealing with larger programs, it will still be doable this way. So we have to subtract a from d to allocate for the space, and then we are going to add register A to register D before we use the return address, because otherwise, if we don't the allocated space used by the local variables, then we'll be using the wrong location as a return address, and then the program, the subroutine, is going to return most likely to the wrong place. I cannot say always, because there's always that rare chance of coincidence that it might actually go back to the right place, but most of the time it's not going to go back to the right place. Alright. Jonathan is to answer Jonathan's question, the labels are not required. But this is the way I write the code, and it is important to understand why I define the labels the way they are defined, because in case in the final exam I give you a piece of code that I'm writing and I ask you to debug the program, well, then it's important to understand how I define the labels, what the labels are used for, and so on and so forth. So the short answer is no, you do not have to use the labels in your own program, but you do have to utilize the stack and the arguments the way they're supposed to be used. So no shortcuts, because in previous years, semesters, some people use the shortcut and go like, oh, I know exactly which location need to be swapped with which other location, and I'll just do that in the swap subroutine. Yeah, almost close to 0 points, in that case, because that defeats the whole purpose of the homework assignment. It does not illustrate that that person understands anything about, how to access parameters and how to perform the operations, specified in C and turn those into assembly instructions. So the next question in the text channel is it useful to think of LDI and sub commands as a kind of scoping for local variable assignments? Well, the LDI is, LDI is just LDI and sub is just sub. So the question is about the effect of these two instructions. What are they doing together, right? They're basically just decreasing the stack pointer by 1 in this case, which is the 1 byte that we need on the stack. Yeah, so in this context, yes. So we are allocating space on the stack for the local variables. And then the other two is really just to undo that, because at the end of the subroutine, we don't need that space anymore. So it is important to deallocate that space. Alrighty. Alright, so at this point, the stack is going to look exactly like this, the frame, because remember these values, the value of the label t is indicating how many bytes is variable t away from where the stack pointer is pointing to. And at this point, this particular picture here, or this particular picture here, is now correct. Okay, without seeing my code, are you referring to the code that I'm writing right now, or are you referring to the sample programs that I did last week? Both days last week. So that question is for Sasha. Alright, so now that we got everything set up, we'll go ahead and implement the first instruction, which is to read from where PTR1 is pointing to, and then copy that value to local variable t. Alright, so this one you can just straight copy and paste from, copy, paste, and modify from the program that we did last week, because there's definitely some place that involves reading from a location pointed to by a pointer. Same stuff, right? So now we just say LDI A, PTR1, add AD, and then we have to do a LDA A. And I'm going to, okay. Okay, I'll get back to that question in just a little bit. So I'm going to do a trick here. I'm going to say LDBA. So this way, register A is the value of the parameter PTR1, and the register B is the content in memory of where it points to. Okay, and I intentionally did not write any comments because I want you to write the comments for this program as you review today's video, or just go back and review the code. You don't have to watch the video again, but I do want you to be the one commenting the code line by line, one by one. That's the recommended activity, and I know some people is going to ignore that and go like, nah, I don't need to do that, or I'm not going to do that. That sounds really boring. I'm not going to do that. That's okay. That is, everybody's choice. Everyone has the right to make that choice. Alright, so now that we get the value in memory that is pointed to by PTR1, we're going to have to copy that to the local variable t. So I need to use another register now. Yeah, good thing we got 3 registers, right? Well, 4 altogether, but since the stack pointer cannot be used for this purpose, now we have to refer to register C. So we got A, C, C, D, like that. And then we do a S, T, C, B. There we go. Alright. Alright, so we got some question or some comments commenting the code that help me reason out the program. Exactly. Because if I did all the commenting and you're just reading it, reading something involves I think it involves a different process and a different part of the brain compared to when you're writing something. And that's why it is different when somebody just gives you everything and you're just reading it, versus you have to write something on your own, and you have to write your own note, because I think it actually exercises different parts of your brain. And to improve your understanding of something, writing or explaining it to somebody else is always going to be helpful. All right. Oh, yeah, all the time. Running out of registers all the time. Okay, so when you run out of registers, what do? You push some of the registers that you don't need right away onto the stack, reuse that register, and then pop that register back when you do need that value back in that register. So yeah, every single architecture only has a certain fixed number of registers, and they are never enough to fit everything in. So you constantly have to kind of be aware of which register is being used, which one is free, and so on and so forth. So there's that. All right, so up to here we have just implemented t equals to asterisk ptr1, and I have to let someone in. There we go. Okay. So now we are going to continue with this code, right? So we move on to the second line. So I have to be careful which register I can indeed reuse. I can reuse register B because register B has whatever PTR1 is pointing to, and we're going to overwrite it this time, so we can reuse register B. We can reuse register C because the second line of the code does not involve T at all, so I don't really need to know the address of T. So we can reuse those two, but I need to keep register A, as it is, because I need to use PTR1 so that I can get to the location that PTR1 is pointing to. Okay, so given all of that stuff, okay, now we just have to kind of do the same thing. Oh, I just said don't use register A, so use register B, and then we do the add BD, and then we do pretty much the same stuff as last time. So we do LDBB. So the B is now the value of the pointer, and then we do it one more time so that we get to, let's do it in a different register this time. Let's do it in register C. Alright, so I am, okay, trust me when I say that I did not pre-write this program and I'm just copying something on the side. I'm just writing the program as we go, okay? So it is important to keep track of the registers, okay? And I intentionally did not write down anything. I did say something, but I did not write down anything, so that you can go back to this program and then track down which register has what at this point of time, okay? And that is really important when you're writing code in assembly code. Are we okay? Let me turn on line numbers. Well, there's only one ST instructions. I'm pretty sure it is line 23. No, line 23 should be STCB because register B has the content, or it has the content of the location that is pointed to by PTR1. So this is exactly what I'm talking about. Okay, yeah, this is exactly what I'm talking about, because you guys need to track down what each register has to understand the program. Now, I did verbally explain that. I mean, yeah. So there we go. All right. So at this point, I got register C being whatever PTR2 is pointing to. and then we got register A being PTR1. So as a store to A from C is going to get the job done. So we are talking about asterisk PTR1 equals asterisk PTR2. This should get the job done. Now obviously I haven't tested the program because I'm just picking this up as we go. But I think this is going to work, okay? And if it doesn't work, it's even better because I can then show you how to debug a program when it doesn't work. I think debugging a program, or knowing how to debug a program, what steps to take, how to reason it out, is at least as important as the concepts themselves. Because as a developer, software engineers tend not to do as much time doing this, but as a developer, I would say maybe 10% of the time, if you're lucky, you'll be writing your own code and go like, yeah, this code is mine. Tech wrote this code. I made my mark in history. But 90% of the time, guess what? You'll be cleaning up somebody else's code that was written 30 years ago with no comments whatsoever. If you're lucky. Because if you're not lucky, then you'll be debugging some really obscure JavaScript code written by somebody who thinks he is a JavaScript guru and use that person would use the most obscure way to express the logic in JavaScript. And trust me, JavaScript can be very good at that sort of stuff. So unfortunately that's kind of reality. Yeah, you can technically create a heap, because a heap is basically just a region of area where you have a free pointer or a free list to keep track of, what segments of memory within that area is free. But since we only have 256 locations to begin with, it's not going to be very effective. We could have one homework assignment just to do some free and malloc and free and malloc and free, and we can create our own tiny little heap fragmentation problem, in the TTP. We could do that, but something that I can think about. All right, so now we're getting to the last one where we need to get back to the value in T. But I also have to be careful which register I can use and which one I cannot use. So right now, register A can be reused because I don't need PTR1 anymore. So register 1 can definitely be reused. I don't need register C anymore because register C has the content in memory that PTR2 is pointing to. So register B is still useful because register B actually has the value of PTR2 itself, and I need that in order to update the location in memory that is pointed to by PTR2. So register B is the one that I need to preserve now. The other two are now available. I just need one of those two, by the way. So LDI, and I can reuse register A in this case with T add AD, and then we do a LDAA, and then we do a STBA, and that should get the job done. So at this point we should have finished the entire swap subroutine. And most of the time I would have completely forgotten that I am supposed to deallocate the local variables. And guess what? I don't have to worry about it because I did it early on. Okay, so whenever I allocate, I automatically write the code to deallocate. In other words, if you're talking about expressions in an infix notation, whenever I use an open paren, I automatically close it. So this way I don't have to worry about pairing the beginning and the end of the parentheses and have to think about, okay, did I close it correctly? Where am I supposed to put the close parentheses? And so on and so forth. This way it's already there. All right. Okay, so there's a heap versus stack discussion in the text channel. Heap is for dynamic memory allocation. That's the technical term, when you use new and delete in C++ or malloc and free in regular C. And then the stack is not directly accessed. The stack is utilized when we write programs like this. We are already using the stack. So they are two, I would say, almost entirely different concepts. They really don't share anything except both are in memory. Alright, so we got the program done, and now we need to append the main program, which is from the question itself. So we'll go ahead and do that. That would be okay. It's just that, to answer the question in the text channel, the label definitions without using the relative thing, it's going to be okay, except, if I choose to have more local variables, then, everything will have to change except for t, possibly, okay? Because, that just bumps everybody down the line. But if I use a relative way to define those labels, then you only have to redefine like one or two of the definitions. The rest will still be correct because they're all relative to each other. Nope, we are not touching the heap in this class. At least not yet. Okay, so now we are ready to we are ready to append the main program into here. So we're going to do a cat plus greater than, which is the append operation. If I had used just a one single greater
We
than, it
can't
would
see
just...
the terminal.
Huh? What?
You're hiding the terminal behind your camera.
Oh, okay. So, yeah, I can't see OBS because I got too many screens up and running. There we go. Okay, now it's good. Or I can just drag it down a little bit. There we go. So now that works too. There we go. All right. So cat greater than is basically saying whatever I type now is going to be appended to the end of this file. So now I can go back to the browser and just select what I need over here. So we have a copy, Control C, go back to the text terminal, and then in this case I have to use Control Shift V because it's a terminal thing, and then paste the content, and then Control D to end. There we go. So I think we got everything here. And now, I need to kind of pull this up just a little bit so you can see the command. So now I'm going to cat swap.ttpasm and pipe it to xclip-cell clip. And Windows actually, interestingly, has a very similar command. I think it's just clip. So if you want to paste something directly from the command line interface into the clipboard as text, you just you use type instead of cat, but you just say type and then whatever file name, and then use the pipe operator, same as this one here, which is a vertical bar, and then you just say clip, and that would put it onto the clipboard in Windows. Alright, so now we got that, and it's ready to go to the assembler. Alright, so I'm just going to delete the entire column A and then paste in the content. Oh, by the way, you want to be careful when you are editing the source code. Don't use the tab character, because if you use the tab character, it will paste into multiple cells in the assembler window, the source window, and that's going to be a problem. Yes, cat is going to work in PowerShell. PowerShell, for the most part, is made to be quite Linux compatible or Unix compatible. Alright, so we can now download CSB, and we'll just change the name to swap.csv. So this way we got all the files starting with the same part of the name. And now that it's done, we can run that long command. And quite obviously I should have made a script to do this already, but I'm too lazy to do it. So we'll go ahead and just copy this portion, and then we say swap.csv, and then redirect the output to swap.tsv. So this way we have the trace ready to go. Unix is now in the new terminal. Yeah, you have to get it from the Windows Store, but it's free, so It doesn't cost you anything. So now we go to sheet 1, go to File, Import, and then we upload the TSV file that we just created a little bit earlier. So I'm hoping most people is using the trace analyzer to help debug this program, because I think the use of the trace analyzer, even if the program is working 100%, using the trace analyzer can be helpful to kind of visualize the execution of the program. Alright, so we replace the current sheet, separator type is tab, and do not do any conversion. Yep, that's PowerShell. I'm referring to the screenshot in the text channel. Alright, so we got everything in, and the analysis is ready. So if you are really confident in your programming skills and go like, yeah, it's probably going to work, then you can all jump all the way to, in this case, row number 237, and that's in the summary tab. So you can just kind of jump straight to 237 if I remember correctly. There we go. The first thing is we notice that the stack pointer is back to 0. That is a good sign. Second thing is we want location 3A to be the halt instruction that we have in the original program. So to get that, you have to go to the Assemble tab. The Assemble tab is actually quite useful. So we can now go to the swap, the halt instruction, and that is indeed at location 3A. So this tells me that even if the program is not behaving correctly, I at least used the stack correctly. So I'm not making any mistakes in terms of not forgetting to deallocate something or deallocating too much and stuff like that. There's always a chance that I did and somehow the problem is masked, but it is unlikely. Okay, so this is always a good sign. So now the actual test of whether the program is working or not is to check those two locations and see whether the content at location FF and the content at location FE are exchanged. So what we do is we go all the way back to the beginning, and then we look at the RAM right column, which is column C, and then we look for operations related to FF and FE. So we can see FE is getting the value of 03, and we can see how FF is getting the value of 07, and they should be exchanged by the time we get to the end of the program. So if I just kind of fast forward and then go backwards from row 237 and go back up, so now we can look at we can see how FF is getting 03, which was the value in FE, and then FE is getting the value of 07, which was the value at FF. So this is a quick verification of the program actually working. But from your perspective, you probably want to kind of do a step-by-step explanation of what each step is doing. Okay, whenever the PC or the program counter changes, you want to look at that and explain, okay, what is going on with this instruction? What does it mean? How does it relate to the C code? And so on. So you can make a copy of this spreadsheet right now. It's already done. If you make a copy right now, you don't have to do your own TSV and then upload it and import it into the trace analyzer. Alright, so I'm just reading the text channel. Why was that a good thing again? Halt's value. It's not the value, it is the location. It's the location of the halt instruction. It is at location 3A. So this combined with the assemble tab in the assembler confirms that we are indeed stopping at the correct halt instruction. Because if you get to a location where it is a undefined opcode, it would still kind of do the same thing as halt, except it is not the proper place to stop and halt the program. So it's important to know that you are indeed halting at the right instruction. All right, so Oh, okay. Well, that means less distraction. Lots of servers are down today. Huh, I wonder why. Alright, so system taking a sick day in quotes. Okay. Alrighty. So that is the program. I do want to make a few comments. The comments has to do with how much understanding I think you should have at this point. Okay, so let me go back to take a look at the source code. I think if you can look at this code and just slowly, don't do it in a rush, okay, and be able to explain every single line and be able to explain what each register is doing, why, what kind of value does it have after the operation, and then relate that back to the original C code, then you are doing okay. On the other hand, if someone tells me and go like, I just see the pattern, this is how we do things, load LDIA with whatever thing that we're trying to access and then add AD, but I don't understand, I have no idea what these two instructions are actually doing. I just know that I just noticed the pattern of doing this, then it may not be such a good thing. Okay, now we still have a few weeks before the final, right? So it means for those people, it's time to catch up with the understanding of the concepts. And there's no easy way to do it. There's really no easy way to do it other than really just kind of going back to the explanation that I have already talked about in class, and slowly go through all of those things and make sure that you understand every single concept, like what is a frame, how local variables and parameters exist on the frame, where's the return address, who put those things on the stack, and how does the called subroutine access that stuff, and then who gets to deallocate which one, and so on and so forth. So all of those things should be clear at this point in this class. Alrighty. Yeah, the Pollens, could have crashed hard drives in the good old days, but these days we have solid state drives and they should be fairly resistant to pollens. Alright, so labels, can I show how to return to main? Absolutely. Okay, yes, we can do that. Okay. Oh, the frame stuff, we did a lab on frames. In fact, we did 2 labs, that talk about frames. So those are the labs are not really just activities for you guys to do, but they also include instructions too. I am not going to repeat those topics, but they are recorded. So you can repeat those topics as many times as you wish by replaying the YouTubes. Okay. Yes, it is recorded. But when you replay it, it will just be me explaining it exactly the same way. So if that's the bottleneck, the way I'm explaining it, then you would have to ask me to explain it in a different way. But then you have to be specific about okay, you mentioned da 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 da. And I can understand it this way, A, or I can understand it like this, B. Which one is it? Okay. Alrighty. Yeah, the return address label is not needed because I have the local var size instead. So it kind of served the same purpose, but not exactly the same. Because I think the necessity to know how many bytes are used for local variables is more relevant compared to where is the return address in the frame. Because we don't really need to know where the return address really is on the stack, because we're supposed to deallocate everything by the end of a subroutine so that the stack pointer is pointing to the return address at that point of the execution of a subroutine, but the size of the number of bytes that we need to allocate for all the local variables is important because we need to allocate and then deallocate for those local variables. Yeah. So there is that. Alrighty. Okay, so that's my comment. So we're going to move on and talk about how to call two subroutines. They both return values, and then we just want to add the return values of those two subroutines. I don't think we have talked about this, so we're going to talk about it now. Alright, so this program is going to be called 12, and I'll do it in C first, and then we'll go ahead and do this in assembly code. When you look at this program in C, you go like, really? Are we really going to be talking about this? But when we implement it in assembly code, there's a trick to get this to work. Okay, so I'll explain that when we get to the assembly code. So the 12 subroutine is going to, the 12 program is going to look like this. We'll do a usual #include stdint.h because I do want to make sure that we are specific about the width of our integers. Oh, we did? We did with Ryan and 5? Oh, okay. Well, then we don't need to talk about it again. Okay. Okay, maybe I'll just talk about it just one more time. Yes, so Sasha has a good memory. Yes, we did talk about that. But I'm going to talk about it just one more time because it is relevant to today's homework assignment. So we have Ryan, which is just going to be returning 7 because Jerry Ryan is the actress of 7 of 9, and hence the subroutine's name. And then we have Johnny, in this case, returning 5 because Johnny 5 is alive. That's the name of the robot in an old movie called Short Circuit. Yes, and I think a lot of programming students really should. It's okay. It has a lot. It has multiple references to programming, right? Because it also has. You can use it to refer to the short-circuited Boolean expression evaluation, otherwise known as lazy evaluation. So, and it's a fun movie to watch too. There we go. And then we say x equals 2 Ryan plus Johnny. There we go. All right. Yes, Chris, you're absolutely correct. You are absolutely correct. Yep, I'm getting old, but not yet retiring. Alright, so here is the C code, and I'm not even going to bother to run the C code. I think all of you know that the value of 12 is going to be stored in the local variable x in main. So now we just do a v-split, okay, vertical split, so that we can write the assembly code on the other side. And we'll call this 12.ttpasm. Alright, so this is going to be a short program, and if you have a photographic memory, it's not even going to be fun because you can remember, oh, okay, we did this already, and it's exactly like this. But I'm going to do it in just a little bit different way. Okay, so we're going to say Ryan. To answer a question that was asked earlier. Okay, so local var size is 0. Well, does that make sense? It makes perfect sense, right? Because there are no local variables whatsoever in the subroutine of Ryan. So we're going to say, okay, well, we'll just use a label to say it is 0. So to answer the question earlier, a label is nothing more than a symbolic name that has an integer value associated with it. So in this case, I'm simply telling the assembler and say, hey, every single time you see Ryan underscore local var size, just make that 0. So it's just a symbolic way of referring to a particular value. Oh, you cannot see the entire Oh, that's because of me. I can move myself too. There we go. Okay. All right. So so from this perspective, if I want to keep the same template of allocating, deallocating, and then return, hey, I can do that, right? Because that makes it kind of it's easier, because now that we have a template, things can be mechanical. So now we can say LDIA with Ryan underscore local var size, and then we subtract this much from the stack pointer to do the allocation, and then we're gonna add this much back to the stack pointer to deallocate the local variables. And we are not supposed to use register A. So to be safe, we use register B in both cases. There we go. And now we have the usual 3 lines of code to return to the caller. So we have LD, BD, increment D, JMP, B. There we go. So I know you guys are very smart. You can definitely recognize the pattern of having these 3 instructions at the end of every single subroutine. But the question is, do you understand what each instruction is doing? Why these 3 instructions together is going to be able to figure out where to go back to in the caller. So that is a question that you really should ask yourself. If you can answer that question and you know exactly what each instruction is doing, then it's good. Okay, that's a good sign. On the other hand, if you just say, well, I just noticed this is how we do things in assembly, but I really don't understand why these 3 instructions are arranged like this, or why I cannot change the order of the instructions and stuff like that, then you need to get a better understanding of how a subroutine returns to the caller. So I'm just explaining basically little checkpoints that you can make for yourself and go like, okay, how do I know that I understand these concepts? So you ask yourself those questions. Okay, so very good, Sasha. Time to kind of try to understand those 3 instructions. I explained those all the way back when we talked about the stack. Okay, so if you want to understand those 3 instructions, you really have to go all the way back to the stack concept module and start with that one. Alright, so now we do a LDIA with 7, because that is the return value. And then now we do the same thing with Johnny. So I'm going to do the very lazy thing, which is copy and paste and modify. So we say 3 to the current line yank, which is the same as copy, and then p, lowercase p for paste after. And then we have to replace all the references to Ryan to Johnny. So we have line 16 to here, line 16 to the current line, change all the references to Ryan to Johnny. There we go. And we just have to change the value of 7 back to 5. So now we have Johnny. Alright, so now all the way to main. Now main is interesting because it does have one local variable x. So as far as main is concerned, it does have local variable x, so the local var size of main is going to be x1 plus. And then we initialize the stack pointer, which is, subdd is one way to do it. And then we have to do the usual thing, which is LDI register. Okay, fine, we'll use B because that's a safe register to use. So we local var size, we subtract B from D, and then we'll do exactly the same thing, except it is an add at the very end, right before the halt instruction, so that we can deallocate the local variable x. So now we just have to call Ryan and then call Johnny and then add their return values together, store that into x, and we are done. Alright, so we'll call Ryan first. That is also a pattern. Okay, so most of you probably recognize the pattern. And now it is time to ask yourselves, do you understand what each instruction is doing? So LDIA with .6+, that's loading the return address. Decrement D to allocate a byte on the stack. STDA to actually copy the return address to the location that we just allocated on the stack. So these 3 lines altogether basically pushed the return address on the stack. JMPI to Ryan first. Okay, so there we go. JMPI to Ryan. And when Ryan comes back, there are no arguments to deallocate from the stack, so we don't have to adjust the stack pointer at all. And then we have to call Johnny. So calling Johnny is going to be the same thing. So the same 4 lines, except the label of the subroutine is not Ryan anymore, and it's going to be Johnny this time. So calling the individual subroutine is not a problem. The problem is they are both going to return the value in register A. So that means right at this point, that register A is important to us, and we need to somehow preserve it. I can easily change this register A to register B. That is not a problem. The problem is, I have, from the perspective of the caller, which is main in this case, I have no idea what kind of register Johnny is going to mess up. Okay? And you guys would go like, but we know exactly what Johnny looks like, right? Because we know the definition of Johnny looks like this, and it doesn't use register C. We could save register A into register C and be done with it. You cannot make that assumption, okay? Because the implementation of a subroutine doesn't have to preserve the registers except for the stack pointer. The other 3 registers, a subroutine can change it any way it wants, okay? So that means we cannot make that assumption that register C can be preserved, is preserved by Johnny. That is funny. Someone can translate a TTPSM program into, turn those into lyrics of a song, and that, I think that would be very funny. All right, so what do? Okay, we need to preserve the return value from Ryan, and yet we cannot use any one of the registers because when we call Johnny, any one of those other registers can be messed up. So the only safe place you can use is the stack. So that is exactly what we're going to do, is to decrement D to allocate 1 more byte on the stack. Well, I shouldn't say 1 more byte, because the byte that we allocated earlier, which is the return address, is already deallocated because the subroutine is responsible to deallocate the return address. So we just basically we use the same location, so that this time we are using it to store the return value of Ryan. So by the time Johnny returns, which is at this point here, the register A now has the return value of Johnny. But the return value of Ryan is actually on the stack right now, so it's time to pop it from the stack. So that means we have to use a LD instruction and put it into one of the registers. Anything other than register A or D is going to be okay, so I'm just going to pick register B. We cannot overwrite register A because register A still has the return value of Johnny. We still need that. Register D is the stack pointer, and this is not an operation that is supposed to change the stack pointer, so we cannot use register D in this LD instruction. And then after we retrieve it from the stack, we have to free that location on the stack. So that means we have to increment D to deallocate that byte that was used to store the return value from Ryan. And now we have register A containing the return value of Johnny, and the register B containing the return value of Ryan. So now we just need an add instruction. So we say add AB. So we're adding B to A. In this specific case, it doesn't really matter, okay? Because we are not returning like in the previous example that Sasha was quoting, because the previous time I was returning 12. Okay, 12 is its own subroutine, so that's why it makes more sense to add B to A. But in this case, I'm not returning Ryan plus Johnny. So if I were to reverse the whole thing and say add BA, it would it will work just fine too. Okay, we just have to remember which register has the value of the right hand side of the assignment, and that's all. Now we also have to make use of the label X, and this is where some of you would go like, yeah, I recognize the pattern of doing something like this. And then we do as STBA in this case, and that should get the program done. Alrighty. So other than the reference to the lyrics of Calling Johnny, I don't see any questions. Okay. Alright, so now we can, once again, check to make sure the program does work. No. LDI A.6 plus is not A plus equal to 6. The dot is referring to the address of the LDI instruction. That's part of the assembler manual. And that's how we can calculate the return address. We explained that when we first talked about the mechanism of calling and returning. Okay, so I am just going to test run this program, and then I can come back and give you guys a few pointers of, okay, in case you're not quite understanding, but you have some idea, some theory of what a particular construct is doing, what are you going to do about that? Okay, so I'll get back to that one in just a little bit. This is TTPSM and xclip. That's clip here. That is correct. Some mnemonics take up 2 bytes instead of 1. There we go. So now the clipboard has the program, and we go back here. And if you did not make a copy earlier, now it's gone. Well, at the end of the class, I can re-upload everything, but right now I need the assembler to work on this particular program. We go to the RAM file, everything looks good, and then we download as a CSV. We call it 12, and then we go back to the command line interface, and now we can rerun the whole thing, except we have to change the swap to 12. Yeah, I know, it kind of makes sense to make a batch file out of this. Just parameterize the name of the CSV file. What can I say? I'm lazy. There we go. Okay, so now, yeah, that makes a lot of sense, right? I mean, okay, so now we have TSV. We go back to the trace analyzer, and a bunch of people are still here. That's good. And don't forget to switch to sheet 1 first, because if you overwrite the other sheet, then you have to make a fresh copy again. So now we go File, Import, and then Upload. This one is 12.tsv. There we go. And this is a fairly short program too. So when we go to summary, it's not surprising. Well, not as short as I thought it would be. It still has 194 rows. So this time, so now the first question is, what should we be expecting, right? Oh, I just, accidentally pressed a key. So the question is, what should we be expecting? What we should be expecting is the value of 12, which is 0C in hexadecimal, to be stored at location FF. Okay, so that would be the most immediate thing that we should be looking at, what we should be looking for. And then from the assembler, we also want to go to the assemble view or the assemble tab to find out where the halt instruction is located. So the halt instruction is located on line 35 this time. So we should be going to the end of the trace and see if 3.5 is the end location. It is. We look at the stack pointer, it is back to 0, 0. So things are looking good so far. Okay, at least the stack is balanced and we did get it all the way to the end of main. So now we're looking for 0C to be stored at location FF. That is the case as well. So I mean, I didn't really trace the program, I didn't explain the program step by step, but I at least got an understanding of what I should be looking for, and those things are indeed in the trace. Alright, so that is kind of what you need to learn to get the next homework assignment done. Let me see what time is. Okay, we still got about 20, maybe 17 minutes. So I will release the lab in, before at around 7 o'clock, and I'll give you a week to work on this one too. Based on the experience of the last program. This time I'll just give you guys a week to do it. But I'm going to promise you there won't be an extension. So that means, you might want to get started with this one like right away, because there is not going to be an extension. Yeah. Well, because it's actually better off if you start the program like tonight, and start to work on it as much as you can before Thursday. So that way, if you run into any specific issue, we can talk about it on Thursday. Now, on the other hand, for people, for some people who want to postpone this, and for whatever reason, I'm not judging characters, okay? I'm simply describing the act of not doing this right away, okay? There might be legitimate reasons, but if people are going to defer this and go like, okay, I'm going to work on this on Sunday or on Monday next week, the problem is we talked about the concept today, and by Sunday, a lot of that stuff is not going to be floating in your mind anymore. Okay, and that makes writing that program so much more difficult, because the context that we have been establishing in today's lecture is gone. So it is really, I think, is a better idea to get started with this one as early as possible, when your mind is still having this context, and then you start to work on it, and then you maintain that context as you go. Okay, instead of waiting all the way until next Monday, where the context has basically completely evaporated from your head, and then it will get much more difficult to do it that way. The passcode? Yeah, well, we'll get to that one. Well, actually, I'm going to do it now so that we don't forget, so that I don't forget, because I do have a tendency to forget to do stuff. Okay. Alright, so it is recursive call. Okay, this is the homework assignment, and I'm going to release it. Alright, so this one has a passcode of FIB, F-I-B, right here, which is the abbreviation of Fibonacci. So I'll make it due in a week. Today is the 20th. So 1 week is going to be the 27th. It's going to do at 5:30 p.m. so that we can talk about it in the lecture. There we go. Alright, save and publish. So now you have access to it. Well, recursion is not any different when you think about the recursive call. The mechanism of the call, how we pass parameters, how we use the return value, and so on and so forth, it is no different from non-recursive calls. The only thing about recursion that is difficult is to debug it, because if you do not specify the condition correctly, you can end up with endless recursion, which then will chew up the space on the stack, and very bad things will happen in that case. Okay, well, they are supposed to talk And yes, supposed to. And even in CISP360, they should touch on recursion at least. At least that's how I taught CISP300 and 360. I don't need any gamer fuel. Okay, obviously this is irrelevant to the class content. When I was a student in computer science, when I was in undergraduate, the homework assignment to me was so much fun that the curiosity and the enthusiasm alone was enough to fuel me to get things done like really fast. I remember I got a compiler homework assignment that was due in 2 weeks. I got it done in 2 days. Just because it was so much fun. It was so much fun. I got it done in 2 days, and then I was bored for 12 days. Sanity is relative. Sanity is relative. Intrinsic motivation. Interesting word. Cool. Alright. So, if you have not been exposed to recursion, it is actually okay, because I did illustrate a recursive subroutine on Thursday last week, right? Because I gave you guys the recursive string length, right? So that's a clue too. That's one clue to how to do this homework assignment. And then the 12 program that I just did today is also another clue to do this homework assignment. So you kind of have to combine those two in some way to get this one to work. The debugging part is going to be the challenging part, okay? Because I almost guarantee that the use of the trace analyzer is almost necessary to get this program done, to debug the program, because otherwise it's pretty hard to track down, where the program went, what location it overwrote, and so on and so forth. So it is really kind of important to learn how to use the trace analyzer and how to use it to debug a program. And to debug a program, it involves two things. One is you have to have an idea of what you think the program should do, and then you have to observe the trace and find out what it actually did. And then you have to look at the difference. Like I think it's supposed to do this, but it went to do that instead. So as soon as you find that difference, the this versus that, okay, then you stop right there, because that is your symptom. Okay, that is the first sign that the program did not do what you thought the program should do. So you stop right there, and then the first question is, how did I get here? And the trace is nice, because if you were to do this in a regular debugger like GDB, by the time you get to the symptom, you wouldn't know how you got there, because there's no trace left behind unless you set up the debugger to do something like that. And most debuggers, are not by default set up to do it because it's expensive to do it. But the trace analyzer gives you every single instruction that executed prior to what you observe as the first symptom that the program didn't do what it was supposed to do. So you basically, at that point, you have to go backwards and find out, how did I get here? Okay, you basically just backtrack until you find the point where it made the wrong decision, or branched to the wrong location, or the stack pointer has the wrong address in it. Then you go like, oh, okay, the stack pointer is wrong at this point. Why is it wrong at this point? Then you go back further, to track down what you did with the stack pointer. Did you add one? Did you subtract one? Did you forget to deallocate something on the stack? That is how you debug a program. And having a trace of everything that led to the point where the symptom happens is really, really helpful. Yes, so when you debug the program, I'm just tracking the text channel here. So Chris is correct. when you test the program, don't test it with fib of 5. Okay, that would not be a good test case to test first. Test it with fib 0 first, then test it with fib 1, because those two are not recursive, and then you test it with fib 2. If fib 0 and fib 1 both are correct, and then fib 2 somehow crashes, or it just went to la la land, then you know it is the recursive case that is the issue, but the non-recursive cases were okay. So so testing the program progressively and writing the program progressively is also important in this case. Yeah, La La Land. I tried to watch that movie, couldn't finish it. I watched the first 15 minutes, which I thought was quite an accomplishment. Alright, just not my kind of movie, that's all. Yes, there is a theorem. It's not a theorem. It really is. Well, okay, it is a theorem, but it is true that everything that is recursive can be done with repetition or iterations, and vice versa. Everything that can be done with a loop can also be done recursively. That is true. But our job is to do it recursively, just to make it very clear. All right, we got about 5 more minutes, and I do want to kind of point out where we are gonna do what we're gonna do now, right? So what we're gonna do now is to look into structures. Yay! Because somebody mentioned in the text channel, I think it's in the general text channel, about structures. So we are going to look into structures and how to make use of structures in assembly code. Which is close to classes. Okay, a struct is kind of like a class. So if you look at the official definition in C++, a struct is a class where all the members are public. I mean, that's kind of it. But you might say, but in C, you cannot have a you cannot have a method in a struct definition in C. You can do that in C++, but not in C. So methods, okay, basically subroutines that are specific to a class, they really are just regular subroutines, okay, except they have a hidden parameter. The hidden parameter is self. So when we use the word self, it is referring to a hidden parameter that is also, that's also pushed on the stack. But it's not visible to you because they want to hide that fact, and that's why it's called object-oriented programming, because we want to look at things from the perspective of the object itself instead of being procedural, where we look at things from the subroutine's own perspective. So when we define okay, so for those of you who are truly interested in implementing classes, we in this class we're not going to touch object-oriented programming, so we're not going to touch classes. There won't be any virtual methods and stuff like that. But for anyone who's interested, I will show you something that you can look up. So it's on the Power Server under My Stuff, Teachers, Modules, and it's something that I wrote a long time ago, and it has to do with C++ class basics, maybe. And I'm gonna take a quick look here. Maybe not this one, and it may be this one here. This is the magic of C++. Okay, I correct myself. What I said earlier about self, SELF, is this. Okay, it's THIS. Obviously I have not been using C++ for a while. Alright, so what is this? Okay, maybe not this one. Okay, somewhere in these notes here is a discussion of how virtual methods are implemented in C++. And I cannot, I mean, you guys can search for it, okay? I'll leave it up to you, those who are curious, to search for that. Basically, that particular module talks about, how we can translate C++ object-oriented concepts into plain C concepts. Now, in this class, we talk about how to translate plain C concepts into assembly code. So if you have the extra layer of translating C++ concepts into regular C concepts, then you would also be able to chain everything from object-oriented programming to what we are teaching in this class, which is assembly language programming. So, and there are some tricky stuff like pointer to functions that you have to understand. Okay, since we have a minute and a half, okay, so I can show you what I mean by a pointer to a function. So when you so a pointer to a function looks like this. When you declare a pointer to a function, if the function returns a void, you just say void, and then you use parentheses to surround the name of the variable. So we'll say, this is a function pointer, and then you can specify the parameters just like usual. Okay, so you can say int x and int y or whatever, right? So what this has defined now is a pointer to a function. So fptr is a pointer to a function, and the function is supposed to take two parameters. They're both integers, x and y, and it is supposed to return a void, which means it has no return value. On the other hand, if you say, I want a function to return a value of some kind of integer, well, just change the return type. So the key really is just this part here. Okay, this part signifies that we are dealing with a pointer to a function. That's it. Yeah. All right, so we are running out of time. The lab keyword is already shared, and let me just type it again. The access code is fib, and then I'll pin it, so this way you guys can just quickly locate the access code to the lab, and that's it. But the preview is on Thursday, unless people have questions about the homework that's going to be due next Tuesday. We'll be starting to talk about structures. Yes, that is your freedom, Aaron. Well, what's the name of the bully in The Simpsons? Which one? Nelson. That's right. So Nelson would say, "To the library." That's what he would have said in this scenario. To the library. And by the way, there's a game arcade. There was a game arcade in Davis called, guess what? The Library. And I think the idea was, kids can tell their parents, the parents would go like, "Hey, Timmy, where are you going?" "I'm going to the library." "Oh, okay, that's fine." "Hey, why do you need all those quarters to go to the library?" I need to make copies of a book that I'm doing research on." Funny. Okay, so lots of overdue books. I like that one too. Okay. Well, I don't think it exists anymore because game consoles are getting inexpensive. Most people play their games on the PC, so game arcades they were not profitable anymore at some point. And renting a place in downtown Davis is expensive, so that place is gone now, I think. Alrighty, so I'm gonna sign off, and I'll be back in about 10 minutes. I do really hope that you guys will start to work on this lab, and I'll see some questions coming in through the text channel. But if I don't see anything, that's gonna be okay too. I will probably, yeah, I'm not gonna say anything. But I do strongly encourage that you guys get on this one early. That's all. Alright, I'm gonna get out of the screen share and also terminate the YouTube stream. And I'll be back in 10 minutes.